Hello. In this lecture series, you will get to see what Mapreduce is, the paradigm, what it is, and we'll look a little bit into the internal details of how Mapreduce scheduling works as well. We'll also see a few examples of how different applications can use Mapreduce, and you'll get to see a little bit of code as well. So in this first lecture here, we'll look at the overall paradigm, and I'll try to introduce you to it from a very basic level. So the terms map and reduce, which comprise the portmanteau term Mapreduce, are borrowed from functional languages such as Lisp. For instance, here's how you would calculate the sum of squares. Suppose you have integers, say 1, 2, 3, and 4, and you want to calculate 1 squared plus 2 squared plus 3 squared plus 4 squared. The map, so first of all, a square is a function which can be applied on any one of these integers, 1 or 2 or 3 or 4, and it leads to the square of the corresponding integers. So square of 1 is 1, square of 2 is 4, square of 3 is 9, and so on. So square takes as input one integer and spews as output one integer. Map essentially is a meta function which applies the function square to a list of inputs. So in this case, 1, 2, 3, and 4 are in a list. This is using functional language terminology. And the output of map square followed by the list is also a list, where the ith element of the list is a square of the ith element of the input list. So map here essentially is a meta function which processes each record. When I say record, I mean integer over here, sequentially in this particular case, but more importantly, it processes it independently. So the square of 1 can be calculated independently from the square of 3, and those two, neither of them follows from the other. So that's the first part. The second part is an addition function which takes as input again a list of the corresponding squares of the integers and just sums them up. Reduce here is again a meta function which applies plus to a group of records. In this case, the records are just integers, and adds them up, and the output in this particular case is just 30. So once again, as far as we are concerned, reduce is a meta function that processes a set of records or a group of records. This may not be all the records, it may be a subset of all the records, and it processes it in batches. So that's a very gentle introduction to how map and reduce work in the small scale. However, if you're given a sample application, a word count, which happens to be one of the more popular applications and widely used applications of Mapreduce, and you're given a huge data set, say all of the text in Wikipedia or all of the text in all of Shakespeare's works, and you're asked to produce a count for every word that appears in that data set. So for instance, the word Richard, which appears in many of Shakespeare's works, how many times does it appear across the entirety of all of the text in Shakespeare's works? You want to produce a count for that. Similarly, you want to produce a count for every single word that appears in that entire data set. How do you do this, especially when you're dealing with large amounts of data, the large amounts of words, the large numbers of words, and the large amounts of text that might be contained in Shakespeare's works? Well, that's where our Mapreduce paradigm comes into play. So the map as a task or as an entity processes individual records. In this case, the records are just words. Each record is a word, to generate intermediate key comma value pairs. Okay, so here I have a simple input file which consists of 4 records or 4 words: welcome everyone, hello everyone. And when map processes this, it produces for each of the records one key value pair. So for instance, for the record welcome, it produces the key value pair welcome, comma 1. This essentially means that the word welcome was encountered once. That's a key value pair. Similarly, everyone, the first everyone generates a key value pair of everyone, comma 1. Hello generates hello, comma 1. And everyone, again, the second occurrence generates everyone, comma 1. This everyone, comma 1, the second one, is independent of the generation of the first everyone, comma 1. So once again, these records can be processed completely independently of each other. In this particular case, I just have one map task, so it runs through these records sequentially, but you can parallelize this process fairly easily, especially when you have a large data set. You can parallelly process individual records to generate intermediate key value pairs, and the output is going to be the same as if you had just one map task. In this example, I have 2 map tasks. The blue one on the top processes the first line of input and produces 2 key value pairs for each of the 2 records in its input. And the bottom green map task produces, again, 2 key value pairs for the 2 records that are in its input. So once again, the output of this is the same as that in the previous slide. If you have a very large data set, you can split up your input data set. You can shard your input data set or split it up and have map tasks assigned to each shard or each split, and the corresponding output will be the same as if you had one map task. Okay, so you process a large number of records by using multiple map tasks. And you can scale up the amount of map tasks with the amount of data. In this particular case, I've just shown each map task being assigned just a couple of words, but of course map tasks are assigned much larger chunks of data, typically in several megabytes, as you'll see later on in this lecture series. Okay, so in this particular case, I have many map tasks processing a fairly large file and producing output, and the output is indistinguishable from when we had just one map task. Why do we have parallel map tasks? Well, it helps speed up the process. So in the ideal case, if you double the number of map tasks, the time to complete all the map tasks will go down by a factor of 2. So you'll process your input twice as fast. So that's the first step of word count, but we still don't have a word count for each word. For instance, everyone which appears twice in this corpus still doesn't have a count 2 associated with it. That's where the reduce comes into play. So the reduce takes as input the output of the map phase. So all the key value pairs that you saw in our small example earlier are reproduced here. This is the output of the map phase, and that is given as input to the reduce phase. The reduce processes and merges, that's the important word here, all the intermediate key value pairs associated on a per key basis. So for instance, here it takes all the key value pairs that have everyone as the key. In this case, there are 2 such key value pairs, and it sums up their values. In this case, the value turns out to be 2. Similarly, it does the same thing for all the key value pairs that have welcome as the key. In this case, there's just one key value pair, and so that output is over here, welcome, 1. Similarly, hello, 1, there's only one instance of it, and that leads to hello, 1. And this is the final output of the reduce phase, and this is the word count that we were looking for. So the word everyone that appears twice is associated with a value of 2. That's over here. Well, again, how do you parallelize this reduce phase? The reduce phase does not process its records independently. In other words, the record everyone, 1, the second record here, and the fourth record here need to be processed together. Their values need to be summed up here. And so this is not independent processing here. Instead, what happens here is that keys are being grouped. Okay, so you want all the key value pairs with one given key to appear at one reduce task so that their values can be merged together. So the way you do this is by assigning keys to reduces. So you assign each key to one reduce. You do this by partitioning the keys. So for instance, in this example over here, the key everyone is assigned to reduce task number 1. And so all the key value pairs that have key equals everyone will arrive at reduce task number 1, which then will sum up the values for that given key and produce the output everyone, 2. Similarly, the keys welcome and hello are assigned to reduce task number 2, which receives those as inputs. For the key hello, it just outputs hello, 1, because that's the only key value pair it's received. And for the key welcome, it outputs welcome, 1. There are different ways of partitioning keys across reduces. In this case, the partitioning has assigned everyone to reduce task 1 and hello and welcome to reduce task 2. One way of partitioning is called hash partitioning. You take the key, you hash it by using a consistent hash function, say simple hash algorithm 1 SHA-1 or message digest 5 MD5 or just any other hash function, as long as it's the same hash function applied to all keys. Then you take modulo the number of reduce servers, the number of servers that are assigned, and that will give you, or the number of reduce tasks in this particular case, and that will give you the reduce server or the reduce task number to which that reduce is assigned. Why do we use hashing? This leads to fairly uniform load balancing of keys across the reduced tasks in the system. Let's look at some code from Hadoop, which is the open source implementation of Mapreduce. Mapreduce, of course, was invented by Google. They never open sourced the original implementation, but they wrote a paper on it and published it. And engineers from Yahoo decided to write an open source implementation of Mapreduce, and that became Apache Hadoop. Apache Hadoop today is widely available and widely used, as many of you know. A company called Hortonworks has been spun off from Yahoo, which does a lot of the code development for Hadoop. So here's what a map might look like in Hadoop. You have a map class which extends a well-known base and implements a well-known interface. It's a templatized interface for those of you who are familiar with the Java language. And the main function here is the map. The map takes as input the key and the value. It also has an output collector and a reporter in case you want to report things to the user. Essentially what it does here is that it takes the value, which in this case is text. So the value might be one line of text in the input file, and it tokenizes it into strings. So here you have the line which is consisting of a collection of strings. Each string is a word. The string tokenizer essentially iterates through all the words. In this case they are tokens, and for each word you output a key value pair, which is that word comma the value 1. Okay? And here we have said that 1 is the new int-writable value over here, and so that's output as the intermediate key value pair. So for every word that you encounter in the line, this map function takes as produces as output that word comma 1 as the intermediate key value pair. Now this line may not be a line, it may in fact be an entire large block of text over here, and the map would work just fine. So what does the reduce look like? Well, you have the reduce class again here, which has one reduce function, and again that has input key, which is text over here, and values, because you may have multiple values associated with the given key. You have multiple values over here. This reduce function is called once for every key that is assigned to that reduce task. So suppose the reduce task is assigned 10 keys. The reduce task is going to call this reduce function 10 times, once for each of the keys that is assigned to it, and the values in that case will be all the values that it has received from the intermediate key value pairs that are associated with that particular key. So for our word count example, essentially this call of reduce will simply go through all the values and sum them up and produce as output a key value pair where the key is the same as the input key and the value is in fact the sum of the input values. And in fact this implementation is a correct working implementation of the word count example that we have seen. So this is as opposed to the previous slide where we had showed the map function, and the map function for instance might be called only once by each map task with all of the input given to that map task as the input to that map function. Now you also have some glue code such as the driver, which has a run function. You specify the job name, in this case it's my word count. You say that the keys are all words by setting your output key class. You also say the values are counts or integers by setting the output value class. You set the mapper class and the reducer class to the ones that we saw in the previous slides. And then you say what the input path is, where do you fetch the data from, and where do you write the data to. As you'll see soon in this lecture series, essentially Hadoop runs on top of a distributed file system, and that's where all the data is stored. The input path name and the output path name are both names of files or directories in the underlying distributed file system. And finally you tell the job to run. Not shown here is the partitioning function, which you can also change in the system. If for instance your data is not easily hashable, or you want to obtain, or you want to do something else like sort, as you'll see soon, you may want to have a hand-tailored partitioning function, and you can change that too in the Hadoop code.